Recent years have seen significant effort and financial investment on technology that could enable efficient use of space resources, alongside advancements in space exploration. Finding the most efficient means to manufacture oxygen on the moon has been at the forefront of these efforts. While the moon has a tenuous atmosphere containing elemental oxygen, it is so thin that scientists refer to it as an airless body. However, there is oxygen in lunar rocks and regolith, the fine powder in rocks that cover the surface. This fine dust, also known as a moon dust, pervades the lunar surface and is the result of billions of years of meteor and comet impacts. As part of the Artemis program, the Australian Space Agency and NASA agreed to deploy an Australian-built rover to the moon. The mission's objective is to gather lunar rocks that may one day be used to create breathable oxygen on the moon. Even though the moon has an atmosphere, but it is relatively thin and primarily made of hydrogen, neon, and argon. It is not the kind of gaseous mixture that might support creatures that depend on oxygen, like humans. Having said that, the moon has an abundance of oxygen. Simply said, it's not a gas. Regolith, the layer of rock and fine dust that covers the moon's surface, is where it is actually trapped. Would the oxygen we could extract from regolith be sufficient to sustain life for humans on the moon? According to John Grant, a soil science professor at Southern Cross University in Australia, the moon's regolith contains about 45% oxygen. These materials' isoptic composition is nearly identical to that of Earth's minerals, leading to hypotheses that the Earth-Moon system evolved together billions of years ago. Many of the minerals in the ground around us contain oxygen. And similar rocks to those found on Earth make up the majority of the moon. The terrain of the moon is dominated by mineral oxides, particularly those of silica, aluminium, iron, and magnesium. Though not in a form that our lungs can access, all of these minerals include oxygen. These minerals are present on the moon in a number of various forms, including the hard rock, dust, gravel, and stones that blanket the surface. This substance was produced over many centuries as a result of meteorites colliding with the lunar surface. The materials on the moon's surface is basically regolith in its original, untouched form. However, that oxygen is tightly bound into the aforementioned minerals. For future astronauts and lunar residents to use that oxygen, it must be extracted from all of that regolith, which demands a large amount of energy to break the molecular bonds. On Earth, electrolysis is widely used to produce metals, in which molten oxides are treated to an electrical current to separate the minerals from the oxygen. The oxygen is produced as a byproduct in this case. However, on the moon, oxygen would be the primary output, with metals saved as a potentially useful byproduct, most likely for habitat construction. As Grant outlined in a recent piece in The Conservation, the procedure is simple, but it faces two main challenges when modified for space. It consumes a lot of energy. It would need to be supported by solar energy or other energy sources available on the moon in order to be sustainable. Extraction of oxygen from regolith would also necessitate large industrial equipment. To begin, we'd need to turn solid metal oxide into liquid metal oxide, either through heat or heat mixed with solvents or electrolytes. We have the technology to achieve this on Earth, but transporting this gear to the moon and generating enough energy to power it will be a formidable task. Space Applications Services, based in Belgium, announced the construction of 3 experimental reactors to improve the process of producing oxygen via electrolysis. They plan to send the technology to the moon as part of the European Space Agency's In Situ Resource Utilization (ISRU) mission by 2025. However, how much oxygen might the moon actually provide if we are successful? As it turns out, quite a bit. We can make some estimates if we ignore the oxygen trapped in the moon's deeper hard rock material and only consider regolith, which is easily accessible on the surface. On average, each cubic meter of lunar regolith contains 1.4 tons of minerals, including approximately 630 kilograms of oxygen. According to NASA, humans require approximately 800 grams of oxygen per day to survive. So 630 kilograms of oxygen would be enough to keep a person alive for about 2 years. NASA planners are working hard to find the best way to produce oxygen gas from all of the elemental oxygen locked up in the moon's surface dust, in preparation for the Artemis missions. In fact, current estimates indicate that the top 10 meters of lunar regolith contains enough elemental oxygen to produce enough oxygen for every person on Earth for the next 100,000 years, more than enough for a lunar settlement. This would also be determined by how efficiently we extracted and used the oxygen. Regardless, this figure is incredible. However, we do have it pretty good here on Earth. And we should do everything we can to protect the blue planet. Please subscribe to my channel and hit the like button.